Let's talk about voltage and current sources. We will begin with the definition for voltage source. Here are some common symbols used for voltage sources. In the first case, you have a plus, minus inside the circle, and there's a voltage attached. There's a number which is a voltage attached to it. Another common symbol is here. This is what you will see in our software. And sometimes this voltage can also be a function of time. Here are some examples. The first example shows a DC voltage source with the value of 5 volts. The second is also a DC voltage source with a value of 20 volts. In the third example, you have a voltage source, but it's not DC because the voltage is changing with respect to time. Sometimes you may also see a symbol like this to represent sinusoidal signals and in general AC signals. 2 points to note about the definition. If you look at the symbol or the notation, there is a plus side or the plus terminal and a minus terminal. The number attached to the symbol is measured according to the voltage at the plus terminal minus the voltage at the minus terminal. Let's look at this example here. This is a voltage source with a plus side and a minus side. Let's call this point A and let's call this point B. And the number attached to it is minus 5 volts. According to the definition, the voltage at the plus side minus the voltage at the minus side should be that number. That means VA minus VB must be equal to minus 5 volts, which implies VB minus VA is 5 volts. So what this is saying here is the voltage at B or B is at a higher potential than A, even though the symbol here says A as plus and B as minus, and the what is at a higher potential is reversed because the voltage value is negative. Consider another example. This time the plus is at B and the minus is at A, and the number attached to the symbol is 5 volts. According to the definition, VB minus VA must be equal to 5 volts. Note that this is same as the case in the previous example. So what this means is both this symbol here or this notation here and this notation here are representing the same source. So if you, in the same voltage source, if you measure from here to here, you will get 5 volts. But if you measure from here to here, you'll get minus 5 volts, right? So the plus minus inside the circle are just telling you how the number attached to that symbol is being measured. Let's look at the definition for a current source. If you look at the symbol, there is a circle and there is an arrow inside the circle. The arrow represents the direction in which the current is being measured. The number attached to the symbol tells you the current flowing in the direction of that arrow. So here are some examples. Here's a current source. Arrow means the current is being measured from bottom to top. So here this means 2 milliamps is flowing from bottom to top. And in this example, minus 3 milliamps is flowing from bottom to top, but that means plus 3 milliamps is flowing from top to bottom. Both the sources we have seen so far, the current sources and the voltage sources, are what are called independent sources. That means the value attached to the voltage value attached to this source, for example, is 5 volts. It is not dependent on any other aspect of the circuit. No matter what happens in the rest of the circuit, the voltage drop across this source will always be 5 volts. Similarly, for example, this particular device here, no matter what happens in the rest of the circuit, the current flowing through this source will always be 2 milliamps. That means these sources are independent of what's happening in the rest of the circuit. Let's now look at dependent sources. We'll start with an example. Consider this setup here. There's a microphone connected to a speaker through an amplifier. Now let's say we want to model this whole thing using a circuit. Here is an example circuit which can model this setup. let's look at the details. At the input side, I have the microphone, which is generating a voltage signal. The box here is the amplifier, and the input voltage generated by the microphone is being fed into the amplifier. At the output side, the same input voltage reappears, but now it is magnified by 100, hence the word amplification. If you just look at the output circuit here, you have a voltage source, and the value attached to the voltage source is not independent of the rest of the circuit. See, the voltage source here depends on what the voltage at the input is. So that is why this is a dependent source. There is some internal circuitry which is happening inside the amplifier, which we're not showing here. Right? We are representing the whole amplifier just with a box. The input side, the microphone, the signal from the microphone is connected to some circuit. It's not hanging out there. This is not open. So 3 dots means there is something else connected here, right? And there is some relationship using that circuitry from the input side to the output side. Now, notice what the amplifier is doing is, so you can ask, okay, if you have this voltage source at the output, where is this voltage getting its power? If the input, if the value is dependent on this, then what is the source? What is the source of the power for this output source, right? And that is coming from the power supply. Note that most often power supplies for amplifiers can be DC power supplies, or when they're AC, they're just simple sinusoidal signals. So what this amplifier is doing, it is converting the power from the input power supply into a signal which looks like the input, right? So that's a non-obvious thing to do, and there are lots of circuits to do that. But the point for us here is to look at where these dependent sources come from, right? So this voltage source, the way this behaves depends on what's happening in the rest of the circuit. Okay, so when that happens, these are called dependent sources. And as far as this circuit is concerned, this microphone is sort of acting like an independent source, right? Because this value does not depend on what's happening in the circuit. It happens on the external environment though, but doesn't depend on the rest of the circuit. This is fixed based on what's happening outside the circuit. So the microphone is an independent source. The voltage source at the output side of the amplifier is a dependent source. Let's look at the notations for dependent sources. So first example here, or the first definition, is a voltage controlled voltage source. Note that for independent sources, they were using circles or sometimes some other symbols, but mostly circles. For independent sources, we'll start using diamond shapes. Note that inside the diamond shape, there is a plus minus. So a voltage is always defined as the difference between 2 points. So whenever you see a plus minus, that means that is a voltage source. And since this is a diamond shape, this is a voltage dependent voltage source or voltage controlled voltage source. So in this case, VI here is voltage at some other point on the circuit, some other part in the circuit. Okay, and the voltage for this source depends on the voltage at that other part. Alpha is just a number. So for example, in this case, in the case of amplifier, the output voltage source is a voltage dependent voltage source, and this 100 is alpha. And this symbol, if I did this correctly, it should not be a circle, this should be a diamond. Here is a symbol for a current dependent voltage source. Again, note that there is a plus and a minus, that means it's a voltage source. As a diamond, that means it's a dependent voltage source. And I1 is a current in some other part of the circuit. Therefore, the value of this source depends on the current in other part of the circuit. So this is called a current dependent voltage source or current controlled voltage source, as we said controlled here. And then this mu, note that this mu is converting current into a voltage. Therefore, mu has units, and it has a unit of ohms. Here is a symbol for voltage controlled current source. Now again, there is an arrow inside the diamond, that means this is a current source. There is a diamond shape, that means it's a dependent current source. And its value is being determined by voltage at some other point on the circuit. So that is why this is voltage controlled current source. G has a unit of current over voltage. That means it has a unit of ohm inverse or Siemens. That means G is acting like conductance. as opposed to mu acting like resistance here. Finally, let's look at current, controlled current source. In there's an arrow, it's a current source. Diamond, it's a controlled or dependent source. The value depends on current in some other part of the circuit, and beta is just a number. Finally, let's talk about the definition of a wire. In any circuits, there are components, and components are connected by wires. So we need to be clear about what we mean when we draw a wire in a circuit. So here's the definition. Whenever there's a wire, what we're saying is all points on the wire are at the same potential. In other words, the voltage difference between any 2 points on a wire is 0. Note that these two statements are independent of the amount of current flowing through the wire. Right? That means the amount of current flowing through the wire depends on what's connected to it. But whenever there are 2 points connected by a wire, we say those 2 points are at the same potential. Now that we define these different components, let's talk about what happens when we put things together. Sometimes when we put multiple components in the same circuit, there can arise a situation which leads to the circuit being invalid. That means not permitted. Okay, so the case when this happens is like this. A circuit is invalid if a contradiction arises from the definition of the components. Let's look at an example. In the circuit here, I'm taking a voltage source with value 1 volts, and I'm connecting the both ends of the voltage source using a wire. Now, according to the definition of this voltage source, VA minus VB should be equal to 1 volts. But if you look at the definition of this wire here, because A and B are connected by a wire, VA minus VB should be equal to 0 volts. That means A and B must be in the same potential. Now, equation 1 and equation 2 cannot be simultaneously true. This is leading to a contradiction. So because we got a contradiction from the definitions of the components in the circuit, we will say that this circuit is not valid. That means this is not permitted. Now, in practice, when you make circuits like this, the wire will usually not have zero resistance like we are assuming in the definition. There will be some resistance. So what happens in practice is there'll be a huge amount of current going through that wire, and something, either the wire will burn or that you'll cause damage to the voltage source itself if there is not sufficient protection inside the voltage source. But in any case, bad things will happen if you do this in practice, so don't do it. But from a mathematical perspective, the circuit is like 1 over 0. So it's not mathematically defined because the definitions lead to a contradiction. So circuits like this we will call invalid. Let's look at another slightly complicated example. Again, according to the 3 amp current source here, the current flowing through this voltage source from top to bottom should be 3 amps. But if you look at the 4 amp current source here, the current going from bottom to top through this voltage source should be 4 amps. So these two statements cannot be simultaneously true. So that means that's a contradiction. So this circuit is not valid. Now, in practice, you should not make circuits like this. In theory, we'll say this is mathematically not defined. So it's an invalid circuit.